All right, so in this video, we're going to learn about some more properties of inverse functions and see some other examples that we're going to do. So make sure you take notes on this video in the handout that's provided, and pause at times to make sure you process what I'm talking about and actually think ahead about what I'm doing, not just listening passively to what I do. Okay, so make sure you write down whatever I write in the video. So recall from the last class that if f of a is equal to b, so if we plug a in for x in the function and get b as the output, what it means is that if we plug b into the inverse, we're going to get a as the output. Okay, so if a goes into f, it comes out of f inverse. If b comes out of f, it goes into f inverse. Okay, so we could say that this a here is the output of f, and a here is the input of f, and b here is going to be the output of f. Then what goes in, again, really emphasizing what goes into the inverse is an output of f. What comes out of the inverse is an input of f. Okay, so those roles swap from the function to its inverse. Okay, so what this means, and I'll illustrate this here in a little bit, is if the point AB is on the graph of y equals f of x, then BA, so input of f inverse, A is the output, then BA is going to be on the graph of the inverse function. Okay, so the x and the y switch. And we can examine that here looking at this graph. So here I have the point 2, 1, which is on the graph of f. If I switch the A and the B, okay, so instead of 2, 1, I have 1, 2, then 1, 2 is going to be on the graph of the inverse. So we can see it's just basically a reflection. So what I've drawn here is the graph of y equals x. So the point 2, 1 on the graph of f just becomes a reflection across the line y equals x to get a point on the graph of the inverse function. Okay, so the graph of f inverse of x, so again, we're flipping all the points of f across the line y equals x to get the graph of the inverse since a and b are switching. So we can view it as that the graph of the inverse is a reflection of the graph of y equals f of x across the line y equals x. Okay, so that's kind of a geometric property that we can think about how the function and its inverse relate to one another. All right, so let's see an example right here. So given this graph of y equals f of x, so I have these points 3, 5, 1, 3, negative 1, 0, and negative 3, 1, I want to sketch the graph of the inverse, which I'm going to get by switching x and y. Okay, so if you want, you can pause and work on this on your own, or you can see me do it here. Okay, so the point 3, 5, I'm going to switch the 3 and the 5, and that's going to give me the point 5, 3 on the inverse. So we have 1, 2, 3, 4, 5, and I'm going to go up 3. So this point right here, okay, ballpark, I don't have a great scale on that. So that point 5, 3 is going to be on the inverse. Similarly, I have the point 1, 3 here on the graph of the original. Well, to get a graph on the inverse, I can switch the 1 and the 3. So the 1 and the 3 on f go to 3, 1 on the inverse. Okay, so this is going to go to the point 1, 2, 3, 1. So that's right around there. So the point 3, 5 connects to 1, 3 on f. That means this point here, 5, 3, is going to connect to this point here on the inverse. So I recommend you kind of doing that one at a time so that you don't have a bunch of points and you're trying to figure out where they go. Okay, so next, so if you need to pause here and rewind, go ahead and do that. But next here, I've got the point 1, 3 connects to the point negative 1, 0. So now I'm going to find out where negative 1, 0 goes. So negative 1, 0 goes to, we switch the x and the y, it goes to 0, negative 1. So that's going to be the point right down here. And so these two are going to connect like this. Okay. Finally, I have the point negative 3, 1. I want to write down what that goes to. We're going to switch the x and the y. This is going to go to 1, negative 3. So this point here, negative 3, 1 is going to go to 1, 1, 2, 3. Okay, so this green graph here is going to be the graph of the inverse function. Okay, so press pause or rewind if it would be helpful to look at this again. Okay, I'm gonna have you actually press pause and work on this example 2 by yourself. So go ahead and press pause. All right, so now I'm gonna show you how to do this one. So the point 5, 2 is going to go to the point 2, 5 in the inverse. So 1, 2, 1, 2, 3, 4, 5. It's going to go to up here. And again, we can think about it as reflecting this point 5, 2 across the line y equals x. Some people like to look at it like that. Then 5, 2 connects to 1, 3. So now I'm going to see where 1, 3 goes. 1, 3 is going to go to 3, 1. And so I'm going to connect this point to the new point, 1, 2, 3, 1. So this point connects like this. And you'll see that any point on the line y equals x is going to stay right where it's at when we reflect across the line y equals x. Okay, now finally this point here, so 1, 3 connected to negative 2, 1. So I need to connect this point to the new point, which is 1, negative 2. So that right there, kind of we can see that is a nice reflection across the line y equals x. So the green graph is going to be the graph of the inverse. Okay, so this is how we get the graph of the inverse if we know the graph of the original function. All right, press pause and work on this one. This one's going to be an interesting one. Okay, so the point 2, negative 1, the point negative 1, 2 goes to the point 2, negative 1, and the point 1, 2 goes to the point 2, 1. So here I have 1, 2, negative 1, and 1, 2, positive 1. So this is going to be the graph of the inverse, which you see is a little different than our previous scenarios there. Actually, it's a little bit similar to the most recent scenario, but what we can see here is we've got kind of like a problem with this function right here. Okay, and the problem is that, so if we ask, sometimes we actually want to ask the question, is the inverse itself a function? And we could see right here that this inverse is not a function, because for example, when x is equal to 1, when x is equal to 2 here, we have a y value up here and a y value down here. For each input of a function, we're not allowed to have 2 different outputs. So in these actually last 3 scenarios, the graph of our inverse is actually not going to be a function itself. Okay, so the answer is no, the graph of the last example is not a function itself. And the answer is because there are inputs in which there are more than one output. Okay, so again, the point 2 has 1 as an output and negative 1 as an output, and that's not allowed in a function. So the inverse still exists, it's just not called a function. I want to make that distinction, okay? The inverse exists, it's just not called a function if the inverse doesn't pass the vertical line test, if you might remember. Okay, so vertical line crosses the graph more than once, so that graph is not the graph of a function. All right, so we have something that we kind of look at to test for that, but we actually also have this definition. So a function is called one-to-one if no horizontal line crosses the graph more than once. Okay, so one-to-one means no horizontal line crosses the graph more than once. So let's test these 2 right here. So is this function one-to-one? Well, in fact, I have a lot of horizontal lines that cross the graph more than once, so this function here is not one-to-one. But this one here, no horizontal line crosses the graph more than once, so this function is one-to-one. So a property that we have to kind of address this short discussion that I was just talking about is that if the function is one-to-one, then its inverse is itself a function. So to reiterate, the inverse exists. The only question is whether or not we get to give it a special name, which is that it is a function. Okay? So again, if we let's look at this last case here. That was our original function, but it wasn't one-to-one because a lot of horizontal lines cross the graph more than once. So since that original function was not one-to-one, I knew right away that even though I could graph the inverse, it wouldn't be a function itself. Okay. All right, so let's just do an example to check that. So pause and work on this one, see whether or not the graph of f of x equals the square root of x is a function. And if you're not sure where to go, I'll give you a hint. We know how to graph y equals the square root of x. Okay, so if we look at the graph, y equals the square root of x, it looks like this. And no horizontal line crosses this graph more than once. So this function is one-to-one. And if a function is one-to-one, its inverse is itself a function. So yes, when I graph the inverse of this, I'm going to get a function. Okay, so note that the process where I draw these horizontal lines, the process for checking for one-to-one, sometimes people call that the horizontal line test. So we're looking to see if any horizontal line crosses the graph more than once. So if the horizontal line, again, crosses the graph more than once, the inverse is not a function. If the horizontal lines all cross the graph at most once, the inverse is a function. Okay, so now we're going to just try a few different types of problems. Okay, so let's start with this one here, and I encourage you to pause and think about it. Okay, so this question is that f of x equals x squared is not one-to-one. So if you remember the graph of y equals x squared, it looks like this. Okay, so that is most definitely not one-to-one. But if we use only half the parabola, then this becomes considered a new function. And if we only use half of it, this new function is one-to-one. And so then its inverse will be a function. So I want to find the equation of the inverse for f of x equals x squared restricted to x is bigger than or equal to 0. Okay, so this is what the graph looks like. Y equals x squared if x is bigger than or equal to 0. So if you haven't already pressed pause and tried it, go ahead and do that now. Okay, so we're going to switch x and y. We get x equals y squared. We need to solve for y. So here we have plus or minus root x equals y if we take the square root of both sides. Okay, you have to remember to put the plus minus when we take the square root. So the question is, does the inverse equal root x or does the inverse equal negative root x? Well, if I think about it as the graph, to get the graph of the inverse, I would take the original and reflect it across the line y equals x. Then I'm going to get, if I reflect all these points, I'm going to get this graph. And this is the graph of y equals the square root of x. So I know I have to take the positive square root there because that matches what the graph of the inverse looks like. So here we would have f inverse of x equals the square root of x. Okay, so again, it was, do I take plus or do I take minus? I need to match what the inverse graph looks like, which is root x, so I need to take the positive root x. Okay, why don't you try this one here? So I'll go ahead and draw the graph. So y equals x minus 1 quantity squared. We're going to shift 1 unit to the right. So that is the graph of the original, but it says restricted to x is greater than or equal to 1. So x is greater than or equal to 1 is this part of it. So we're going to get rid of all of that. And then on this new interval, the function is one-to-one. we could talk about finding its equation. So like in the last problem, we're going to, we have here y equals x minus 1 quantity squared. We switch x and y. Take the square root of both sides, so then we need plus or minus, so square root, but we need plus or minus square root of x equals root y minus 1 squared, so y minus 1. And like the last case, since this is kind of similar, opens up, we're going to, if we reflect it across the line y equals x, we're going to end up still needing to take the positive side. So in this case, we took the positive square root. So in this case here, we also take the positive square root. So here we will take root x equals y minus 1. So take positive. Since it's the right half of this upward facing parabola, so then we have add 1 to both sides. So we get y equals root x plus 1, or f inverse of x equals root x plus 1. Cool. Okay, remember you can always go back and re-listen to an explanation. So finally, one last type of problem that I want to do with you here is to find the equation of the inverse function. So I have y equals 3 over 6x plus 1. So I'm going to switch x and y. So x equals 3 over 6y plus 1. Now what I'm going to do is I need to get the y out of the denominator. So I'm going to multiply both sides by 6y plus 1. So then if I take 3 over 6y plus 1 times 6y plus 1, that's 6y plus 1 cancels, because this is like over 1. So then 3 times 6y plus 1 over 6y plus 1 times 1, that's going to be a factor that cancels. So then I have 6y plus 1 times x equals 3, and now I'm going to distribute on this left side. So I have 6y times x, so 6yx plus 1 times x, so plus x equals 3. And now I want to solve for y, so anything that doesn't have a y, which is this, I'm going to bring over to the right side. So I'm going to subtract x, and then I get 6yx equals 3 minus x. And then finally I want to divide, I want to isolate y, so I'm going to divide both sides by 6x. Oops, 6x. So I get the 6 cancels and the x cancels. So I get y equals 3 minus x over 6x. So that's what my inverse here is. Okay, so this one is pretty similar. Press pause and work on it. So we get x equals 2 divided by 3y plus 6, multiply both sides by 3y plus 6. Cancels on the right side. So we get 3y plus 6 times x equals 2. Distribute on the left. So x times 3y, I can write it as 3xy or 3y. Distribute the x to the 6 as well, so plus 6x equals 2. And then like before, I want to solve for y, I want to isolate y, so I'm going to subtract 6x from both sides. So anything that doesn't have a y, I move to the right. So then this becomes 3xy equals 2 minus 6x. And then like before, I'm going to divide both sides by 3x to isolate y. So then those cancel, and I get y equals 2 minus 6x over 3x, or f inverse of x is 2 minus 6x over 3x.